Good evening, everyone. Welcome to the second session of the day. I am Sri Krishna Sudhamsu, a postdoctoral researcher from the Department of Applied Mechanics, IIT Madras. Today, I am fortunate to have the opportunity to introduce the speaker of this session, Dr. Sushma Santapuri. Dr. Santapuri is an assistant professor in the Department of Applied Mechanics at the Indian Institute of Technology, Delhi, since July 2016. Prior to joining IIT Delhi, Dr. Santapuri worked as a visiting scholar at the University of California, Berkeley, and assistant professor at the Polytechnic University of Puerto Rico. She received her PhD in mechanical engineering from the Ohio State University in 2013 and BTech from Indian Institute of Technology, Madras in 2007. Her research is focused on mechanics of electromagnetoelastic materials, soft active materials, and their applications to soft robotics, sensors, and actuator devices, and energy harvesting. She authored 17 international journals, journal papers, and conference publications, and 2 book chapters. It is my honor to introduce her in this platform, and I welcome her today to present the talk on thermodynamic modeling of magnetostrictive materials and their applications.
Thank you, Dr. Sudhamsu, for the introduction. Hello all. Maybe I'll just start. Do full screen mode. Yeah. So I think this talk is maybe going a little bit away from the inelastic response, wherein we are working towards modeling materials that are that exhibit coupling, external field based coupling, right? So I'll start today by just giving an introduction or an overview of what magnetostrictive materials are, and then how do we go about developing a free energy model of these materials, and then how do we develop from this information, the problem, one of the key problems that we face when we are modeling magnetostrictive materials is the response is highly nonlinear. In addition to the magnetic field and mechanical response, coupling between the magnetic field and the mechanical response, the response is highly nonlinear, and then it becomes very difficult, despite a lot of potential that these materials have in towards using them for applications. Because of this inherent nonlinearity and coupling, it becomes a little bit of an issue if we want to develop finite element codes using these materials and to put them towards tangibly towards some application. So then I'm gonna discuss a little bit about what we had done, how our work on how to make these models more computationally efficient, and then I'm gonna show one application, for a transducer device, and with that, then I think we can, go on to questions and discussion. Before I start here, can I ask a quick clarification? And is the talk supposed to go on for 1 hour or about 40 minutes?
Total duration for this session is 1 hour.
1 hour.
So
Okay.
you can choose how to.
All right. Okay, sir. So first, I'll start by introducing what is magnetostriction. So magnetostriction is this phenomena that occurs in ferromagnetic materials. Ferromagnetic materials, the easiest or the most common that we know of is iron. When we apply a magnetic field, and what happens is that the material stretches along the direction of the magnetic field. There is a shape change as a result of the applied magnetic field, and that effectively means that through a non-contact we can apply a magnetic field without actually having any contact with the actual body, with the actual ferromagnetic body, and we are able to make an actuator out of it. I'm a little bit overstating here. When we talk about actuator, how much expansion, that is where that is important, right? So it happens that all ferromagnetic materials have this exert magnetostriction, but the order is extremely low. The reason why we don't use iron in actuators is because the magnetostriction that comes out of it is so negligible that you can't make a decent device out of it. But there have been material scientists who have worked hard in the last century or so to come up with two very prominently used magnetostrictive materials, terphenol D and galphenol, which show quite significant effect. Okay, so the magnetostriction is quite significant for these materials, and there are two plots of importance here. So change in length per unit length as a function of applied magnetic field, as one can see. This applied magnetic field, as we keep increasing the field, we can see that the material keeps on stretching, increasing in length, or there is a normal strain, and it keeps on the strain keeps on increasing until a certain point, after which the response kind of saturates. Okay, so there is a limiting field after which we will not see the material extending any further. And the same thing happens when we want to study the magnetization, right? Magnetization of the material. What happens to the magnetization of the material as we keep on increasing the magnetic field? How do we visualize magnetization? It's somewhat the way to think about it is just the magnetic strength of if we think of a piece of iron, or like take a permanent magnet, we talk about magnetic strength. Magnetization is in a way quantifying that, okay, the magnetic strength of that material. And also it is fairly well known to us that when you keep a permanent so sometimes iron on its own is not magnetic, but when we keep it next to next to a magnet, next to a permanent magnet, it starts behaving like a magnet. Effectively we are doing this, we are applying a magnetic field and we are magnetizing the material. For small magnetic field there will be a little bit of magnetization. If we apply large magnetic fields, there will be significant magnetization. However, this effect also seems to saturate. Okay, so what happens, what happens within the material that gives us this type of effect? And I think that is what majority of the talk today will be about. And then I'm going to talk about how to quantify it in numbers, how to quantify that effect in numbers. I talked about how external magnetic field gives rise to strain, and this strain which is induced only due to the applied magnetic field. So there is no mechanical force here, a strain that is purely so there is no elasticity concept here. There is no elasticity of the material, or mechanical response of the material doesn't come into play. What matters is just the applied magnetic field, which is then stretching the body. Okay, then the opposite effect also happens. So this effect that I just talked about is the Joule effect. There is an inverse effect also. So when I apply stress externally, it magnetizes the body. Okay, so here I talked about magnetic field giving rise to magnetization. One can also magnetize the material by applying stresses, but of course it matters the direction of stress relative to the to certain important directions of the magnetic of the ferromagnetic material, which are I'm sort of I'll explain this a little bit more. The direction of the stress really matters here. Okay, so that's the big takeaway. So here as I spoke about earlier, all the important materials and their magnetostriction values. So this is parts per million, 10 to the power minus 6. The value is as small as 10 to the power minus 6. Iron, nickel, and these are more recently alloys have been made. The galphenol, we use galphenol quite a bit in our research. So this is gallium and iron alloy, and this is moderate magnetostriction, 450 times 10 to the power minus 6. That's the amount of strain that is generated. This is the maximum, by the way. When we talk about number like this is the saturation strain. So this this is still far lower than what we see for terphenol D, but galphenol is much better in its mechanical robustness, in a sense that it won't it's not as brittle as terphenol. That if for very and with terphenol, to keep it to make sure that it doesn't break during device operation, we always keep it pre-stressed. So I think, so in that sense, galphenol, the damage aspect is, we have to worry about it a little less than terphenol. Okay, so this is one. Now I'm going to talk about the physical origin, why magnetostriction happens in materials, In fact, more specifically, there is a phenomena called domain formation that is seen in ferromagnetic materials. So the domain formation happens when you have so typically what happens is that there is a so when we apply a magnetic field, one can think of each, like so this is the atomic picture that I'm showing here. The nucleus and the electron each have their own magnetic moment. Just think of, like, combination of north and south poles, like tiny little magnets that are associated with each of these. How these moments orient, they will want to rotate towards the direction of the magnetic field. Okay, and overall, it also matters, the symmetry of the crystal also matters here. So what happens is that when we apply magnetic field, or let's say what happens in the absence of magnetic field. So if there are no magnetic fields, if we look at the microstructure of a magnetic material, we'll see that it will have these type of domains where the arrows point to magnetic moments within each of these domains. So within each region of same color, sort of, the domains, all the magnetic moments are oriented in the same direction. So you can think that each domain is comprised of such tiny little magnets that are all pointing in the same direction. And overall, there are some, I mean, they're not all possible directions. There are some fixed directions along which these domains of uniform magnetization are formed within the magnetic material. And why does this happen, right? So this happens because it's energetically favorable for the material. Okay, and when I say energetically favorable, I think mathematically I'm going to show how that works out by the end of the lecture. So so what happens is when there is no magnetic field, the domains orient themselves along what's called the easy axis. Okay, so the easy axis for a material with cubic crystal symmetry, the easy axis is along 100, and it would take a lot more magnetic field. So if I apply a magnetic field in one of these, I mean, if you see this triangular bracket, this means plus or minus 100, 010001, right? All possible directions. So that's what we see in this image. All 6 of these possibilities. Now, if we apply magnetic field along any one of these, the material will magnetize very quickly. Okay, so the material will magnetize very quickly. But if we want to, or saturate, right? I mean, I talked about saturation. So when I say a material is fully magnetized, it means that it has saturated. Now, if we apply a magnetic field along 111, it'll be a lot harder. It will saturate, but it will be a lot harder for for the magnetic field, for the magnetization to reach its saturation value. And of course, there is something in between also. So all other directions would be in between the easy and the hard axis. Now, with this image, now let's see what happens, right? I mean, I gave a rough overview. What happens to the domains as we keep on applying magnetic field in a certain direction? Okay, so initially, as we can see in this sort of a cartoon figure, we have magnetization along easy axis of the crystal, and there is no magnetic field. Net magnetization, which is sum of all the magnetic moments in the entire volume, that would be 0. Okay, now we keep on increasing magnetic field here, right? Slowly keep on increasing the direction of the magnetic field. As one can see, we've just chosen some direction, and the domains that are oriented favorably to the magnetic field direction, right? So in other words, if I try to calculate the angle between the magnetic field and the domain, whichever ones are closest to the magnetic field, oriented, closest to the magnetic field orientation, will grow. Okay, will grow at the expense of others. So the others which are unfavorably oriented, so to speak, will start reducing in size. Okay, so then still one can see that up until this point, increasing magnetic field is not causing the domains to rotate, right? There is only domain growth that is happening until moderate field value. Okay, until the field value is moderate. Then after this point, when I enforce it further, right, when I apply, keep on increasing the magnetic field a little bit more. So right now only the favorable domains have remained, up until this point, only the favorable domains have remained. But now if I further apply, further increase the magnetic field strength, the domains will start to rotate. Okay, they'll keep on rotating until all the domains are fully aligned with the applied magnetic field. Okay, and this magnetization strength, this is constant. Magnetization strength, ms, is a constant value for a material. Okay, now after saturation, so one can see that since magnetization, as we define it, is a vector sum of all of these magnetic moments within each domain. In here it will be 0, and then this will start to become non-zero as we keep on increasing the magnetic field, and it will be maximum once the field saturates. Okay, now so this in the process of domain growth and domain rotations, the domains also stretch. Okay, so the domains also, there is a shape change. The domains, because we are causing this rotation, the domains have to realign themselves, and when that happens, there is a shape change that happens, and that's the reason why we see magnetostriction. Okay, so I also talked about the inverse effect, so where stress induced anisotropy is observed in the materials. Okay, so so what happens is, again, we'll start with the sort of very similar this thing. We have our initially net magnetization is 0. Now I'm applying stress in a direction that is perpendicular to a few of these, but parallel to some of these, right? So when I again keep on increasing the value of strength, so value of stress, then the domains that are perpendicular to the stress will start to vanish, and then the ones that are aligned with the direction of the normal stress will grow. Okay, so this is how again, so in the process from here to here, we have changed the magnetization of the material. So so this is what I think the major takeaway is, that one can induce magnetization in the material based on stress or based on, or applying magnetic field. Okay, and this, again, the stress induced anisotropy is significant in magnetostrictive materials, not so much in most ferromagnetic materials. This is fairly negligible, but only in magnetostrictive materials, this is the inverse of the magnetostriction effect. This effect is the inverse of it. So they are only considerably, or they're dominant only when so only in magnetostrictive materials. Okay, so then with these properties, the materials have a lot of applications. Okay, so we can use it. We can use this, use all of these properties to develop actuators. So I think inchworm actuator is something that we know that these sort of actuators exist in piezoelectric materials. I mean, I'm not gonna go into details of it, but what's interesting here is that the magnetic field strength, as as each coil gets activated, so one can see when the coil 1 gets activated, magnetic field is applied, magnetic field is generated here. One part of the rod will stretch, and so on. So we can sort of, by we control the actuation in the rod by playing with the different coil currents. So this is how inchworm actuator works. Then we can also use it for vibration control type applications. So where, and again, like most of these applications have been I mean, they exist for piezoelectric materials, and the counterparts for magnetostrictive materials can be designed. There is a pro and a con here. When I mean, so for those of you who have some idea of applications related to piezoelectric materials, we need to apply voltage, right? We need to apply voltage directly on the, so we think of a dielectric material. We are applying a voltage difference across the thickness, and then there may be some deformation, which is what which is what an actuator is, right? And the inverse also, that when we apply forces, those forces can be sensed, because when a force is applied in a piezoelectric material, that results in a voltage, right? So that voltage can be sensed. So effectively we are sensing the force. But the problem is that piezoelectric materials are I mean, we cannot design a sensor which is non-contact. You will have to paste this sensor on the material to be able to sense it, right? So whereas we can design, so for example, if you think of a magnetostrictive sensor, it can you can do a non-contact sensor also. We can design a non-contact sensor because change in magnetic field can be picked up from anywhere. Okay, so magnetostrictive material, when we apply force on it, when we apply any kind of force on a magnetostrictive material, it changes the magnetic flux surrounding it, and that would be easily picked up by a non-contact sensor. The flip side here is that contact versus non-contact. The flip side here is that we the setup is usually heavy, right? We will always need to have coils that are large enough where you can apply the required amount of magnetic field, and coils or permanent magnets, which make the setup bulky, okay, somewhat bulky. So the design, the system design has to be done carefully. So this is, these are the pros and cons. But one of the main challenges where magnetostrictive materials are at a disadvantage compared to piezoelectric materials is that the material response in magnetostrictives is non-linear. And whereas piezoelectric materials are inherently linear up to a large extent, right? I mean, we design a device within the operating regime of the device. Piezoelectric materials are linear. So here what happens is, then this non-linearity, when we want to design a device, in addition to our experiments and the test setup, we need, it is always beneficial to have models, reasonably accurate mathematical models that can be used to do parametric analysis, right? So that we can improve on the design computationally, instead of having to, conduct several experiments, keep on tweaking the geometric parameters or the material property. If we have a reasonably good, fast but reasonably accurate models, they can be used to do a faster device design. And this is where I think the crux of today's, a lot of the research on magnetostrictive materials these days is focused on making the system, making the models computationally efficient, while retaining the non-linearity, or while retaining the inherent complexity. So some of the complexity we want to retain, the important aspects, some of which I have touched upon when I was describing the material behavior. Okay, so then when we talk about this material system design, to improve, as I was saying before, we need to characterize the materials correctly. This has been done actually long ago for magnetostrictive materials. No characterization data is available from at least a few decades ago. People have developed nice experiments, and we have all the data that we need, and then models both. We want to develop, we want sorry, when I talk about characterization, there are two aspects here: experiments and the material model, so the constitutive models, right? So in addition to this, there is the system level model, meaning your governing equations that are valid for all materials, right? So in this case, we will have conservation of linear momentum, angular momentum, etc. And then there would be magnetic, magnetostatic governing equations, which are Maxwell equations, like the Gauss's law. So these, together with the material constitutive equations, will be used to will be used to perform the structural analysis. And then also it is beneficial to reduce it, right? I mean, we don't developing a 3D model has in terms of we are just increasing the computational efficiency, we are increasing the computational effort, because most of the devices that we see are typically either a beam or a rod or a plate. So reducing them to a lower order gives us computational efficiency, a better understanding of the system, and of course better for design overall. So
Madam,
this
can
is
I ask a small
sure.
clarification?
Yes, Professor Rao, yeah, go ahead.
I just want to know, when you say non-linearity, is it reversible non-linearity or irreversible non-linearity?
So here the non-linearity is actually it's a very good question. I did not touch upon that. For the case of if there is no dynamics involved, meaning the applied field is of low frequency, then it is fairly reversible. Okay, so the hysteresis that comes up here is hysteresis that we see here is reversible. Okay, but what happens is that if the applied magnetic field is and also like this, so once we it's an interesting question. So once this saturation happens, if we remove the magnetic field, it will go back to its original state, unless this process is made permanent only if some sort of heat treatment is done in addition to prolonged exposure to external magnetic field. Only then the process becomes irreversible. So typically for low frequency, inputs, this is reversible. This non-linearity is reversible.
Thank you.
So yeah, I mean, as far as I understand, actually we call that anhysteretic response. So hysteresis starts to show up as the frequency of the input field increases, and that is also an important aspect to be modeled. And that, I mean, which I don't talk about today, but it's also something that has to be incorporated within the model, and a very important aspect at that. So actually, I will touch upon that a little bit, later. There is a nice plot which shows where the loading and unloading paths are also different here. Okay, so I hope that answers your question.
Thank you.
Hello.
Thank you. Please go ahead.
Yeah, sure. So once we can successfully do this, develop good material models, and also have asymptotic models of reduced order, we can then take them towards applications. Okay, so this is actually the what we talked about. Now if we so initial magnetization curve, this is what we were talking about. And what happens is that when we unload, and again this effect is more and more prominent when the applied field is dynamic, but when we unload it, it follows a different path. And then when we load it again, then it follows a different path. But then after a certain point, it sort of settles down. This loop kind of settles down, and the hysteresis is reasonably large. Again, like I said, when the frequency is large. And for low frequencies, this is there is some hysteresis. Yes, there is always going to be some hysteresis, but it is negligible, and we typically model the material using an hysteretic response. Okay, so that is what I'm gonna show the model, the free energy models that have been developed in literature, and those are modeled assuming an hysteretic response. Okay, so the two the modeling challenges that are that exist are that the response is non-linear, and then there is hysteresis to be accounted for. Now then in this type of framework, typically we have internal variables involved, internal variables that are specific to the material or to the microstructure of the material. So in this case, the internal variable of interest is the magnetic moment, right? Or magnetic moment, small m. It's I had the definition somewhere, maybe it's all right. So I think it'll come up a bit later. So the magnetization, the total magnetization I mean, I talked about this in my previous slide. I'll just, yeah, so right here, net magnet, sum of all the magnetic moments is the magnetization. So we define, there is a small m, which is defined as capital M, the vector, magnetization vector, divided by its magnitude ms. Okay, so ms is the magnetization. So this small m, what we call the magnetic moment, or it's also called so it's the magnetic moment. So this simply becomes orientation. So when I do this m divided by ms, then this is simply the orientation of the magnetic moment within the domain. Okay, so this is simply the orientation. So it's a unit vector. This small m becomes a unit vector. Okay, so this is the internal variable that we use in developing our material model. In addition to the input field, in addition to the mechanical, the stress or strain, whatever mechanical variable we take into consideration, in addition to that, there is this internal variable that is incorporated within the model. So yeah, then now how do we develop the constitutive model? Typically, when we want to write the internal energy in case of a linear elastic material, in fact, for any material, the first thing we like to do is, if possible, we would like to obtain its strain energy, right? And in the similar way, here, of course, it's not just strain energy because it's not purely mechanical. There are several components to it. And probably I should have added that so this, which I have sort of neglected, because U elastic also should be here, which is again very similar to our strain energy. Okay. I mean, or exactly the same as our strain energy. Now, all the other terms that are involved, we have the magnetic anisotropy, and I'll explain each of these in more detail. So if I want to define the total energy of a magnetostrictive material, there is the anisotropy energy, and this is magnetic anisotropy, by the way, magnetocrystalline anisotropy to be more specific. Then there is the magnetoelastic energy, which gives us the coupling effect. So when we apply stress, the material magnetizes, or when I apply magnetic field, the material changes its shape. Those effects will be given by this term, this energy term will be explained by this energy term. Then there is the exchange energy. It's a little bit tricky. This energy is all about what happens at the boundaries of these two. Okay, what happens at the boundaries of the domains. So the energy is related to that. And then there is magnetostatic energy. The magnetostatic energy, I'll explain it. It's about it's also called, it also tells us about demagnetization that happens in the material. Okay, so this is related to that. And the Zeeman energy is the external field, is related to the external field that you apply, right? So I'll go through each of these, and then we can see how this would explain some of the phenomena that are observed in these materials. Okay, so first I'm going to talk about exchange energy. So this energy is zero within a domain. Okay, so inside one domain, this energy is zero. So this, as one can imagine, if the material was isotropic, okay, if the material was isotropic, there would be only one domain in the material. Okay, one or two, one and the other one in the opposite direction, such that the net magnetization is zero, right? So there will be but materials, magnetic materials are anisotropic. So what happens is that at the boundary, there is a gradient of magnetization. There is a change in magnetization, and what the way it happens is that, so the magnetic moments are all oriented in one direction in a certain domain, and at the boundary of the two domains, what we call the domain wall, the magnetization doesn't, I mean, it won't flip suddenly, right? I mean, it will not go from +1 to -1 suddenly. There is a region, there is a small region where the magnetic moments gradually move from one direction to another. And there is a penalty to that. Because of that, that there is a penalty to the energy, which is given by exchange energy. I'm not going to talk a lot about this, because at macro scale, the the gradient effects are negligible actually. The effect of this term is negligible, and one can correlate with what happens, why this happens. Gradient effects, I mean, we some of you may have worked on even gradient elasticity theories. Gradient elasticity theories or flexoelectric effects. So these sort of gradient effects are negligible when we talk about samples in the scale of a few micron or nanoscales. But in the kind of applications that I was talking about, where your sample is at a macro scale, gradient effects are usually far less. So the penalty to energy is negligible compared to the other terms that are involved. Now, then coming to Zeeman energy, and this is interesting. This term, I think for mechanical engineers, we can relate this to the external force term in energy. Okay, so when you're so maybe you'll write the potential energy expression, and then you'll try to minimize the potential energy in like a variational approach. In the variational approach, let's say, so there we write this external force term minus F external dot displacement. So this is very analogous to that. I mean, as far as for me, I see that this sort of analogy, that when I apply an external field, so HA is the applied field or external field, and in the presence of this applied field, of course, this is what magnetization is all about, that domains that are favorably oriented to the magnetic field. So HA dot M, right? I mean, as close it is to 1, the higher will be this term. Okay, so higher will be the magnitude of this term. So that is what Zeeman energy tells us. Then the next is the magnetostatic energy. Now, magnetostatic energy, so let's say we place, you have this applied field, we place a magnetic material in the external field. Then the total field surrounding the magnetic surrounding the magnetic material does not remain equal to applied field, because the presence of magnetic medium changes the field around. Okay, so the total field, if say when we try to measure the field, the total field will be the sum of this applied or the external field plus the self field. This is also called the demagnetizing field. Self field that is created by the magnetic material in response to the applied field. Okay, so this distortion, it's also like it can be also seen as a distortion. It will be of a smaller order compared to the applied field, and domain formations actually play a major role. What happens is that if there are more and more domains of a certain kind, if we have opposing domains arranged in a certain pattern, the demagnetizing field becomes smaller and smaller, like more and more negligible. So so this is another term that is often neglected, especially for the magnetostrictive materials that we use. This term is negligible for the same reason what I'm telling, what I've shown in this picture, that this is also called the stray energy, by the way, right? I mean, energy due to the stray fields. So the stray field or the demagnetizing field becomes very, very small once we if for depending on the domain patterns or the arrangement. And so this is another effect that is usually neglected in our models. Okay, so then magnetoelastic energy. So this is the most important one when we talk about coupling. Okay, so this term incorporates two effects. One, magnetostriction, where presence of a magnetic field will cause elongation. So one can see what is happening to the domains, right? So each domain is marked with a certain shape and an arrow. Arrow is the direction of the magnetic moment within that domain. And as we apply magnetic field, all the domains orient themselves, and in the process end up causing an elongation. Okay, so this is one, magnetostriction. This is a pictorial depiction of that. Then there is stress induced anisotropy. This also something that I explained earlier, right? That when you apply stress in certain directions, this magnetizes the material in response. So the energy corresponding to this, here I have only shown like a uniaxial term. uniaxial loading term, but we can make it more generalized. Actually, it's there in one of my recent papers, the 3D version of this. I mean, just for better understanding, I've shown a uniaxial treatment here. Lambda S is the saturation magnetostriction. So the maximum magnetostriction at saturation. Sigma is the magnitude of the stress that is applied in case of uniaxial loading. And sine theta is the angle between the sine theta is the angle between mm, uh, the stress and the magnetization. Okay, so the angle between stress and magnetization. So this is one. And what happened here? 1 second. Suddenly this equation moved. Okay, so yeah, so the last energy is magnetocrystalline energy, and the one that explains all of this. I mean, I've gone through the whole process of magnetocrystalline energy and magnetic anisotropy, meaning when we magnetize, when we apply magnetic field along the easy axis, saturation is quick. When we apply magnetic field along the hard axis, it takes a while for it to saturate, or in other words, it takes larger magnetic fields for it to reach saturation, right? So the energy that the term for energy that explains this, or that is able to explain this phenomena, saturation and increase in magnetization with increasing magnetic field, and those terms are incorporated within this. Okay, so here this is like a phenomenological model where we are allowing this to depend on the magnetization vector that I talked about, or the small m, which is a unit vector. Small m is capital M divided by ms, right? So capital M divided by ms. So this, because it's a unit vector, we can write it in terms of the direction cosines, right? So theta and phi. So by doing this, what we are doing is, instead of working with three variables, m1, m2, m3, now we have to just work with these two polar angles, theta and phi. Okay, so let's say we have a generalized expression like this. Now one can go on and reduce this. Again, very similar to what we do in linear elasticity. If just to recall, that depending on isotropy, we reduce the elasticity tensor, right? I mean, so we first have the expression. If we know that it is linear elastic, then we say that sigma is c times epsilon, where c is a fourth order tensor with several constants. And in order to reduce or to find the minimum number of constants, we apply symmetry operations, right? So the same thing happens here. So I'm going to spend the next few minutes just talking about the different, how symmetry operations are done to reduce these terms, but only very briefly, because I see that I'm running out of time. Okay, so I think, hello. Yeah. So, so the first thing is, I'm going to show how to reduce it for a cubic crystal. Okay. So there are, several symmetry operations. So for example, in case of isotropic materials, is the audio are you all able to hear the audio from this that is coming from here? Is it audible?
Yes, hear you very well.
Okay, so I just want to play this small thing, fourfold crystal symmetry. Yeah, so when when we do a rotation about 001 axis in a cubic crystal, the cube matches itself for every 90 degrees. So that is a fourfold crystal symmetry. So this symmetry has to be retained in the energy, right? In the free energy expression, so that is, so we apply these type of symmetry arguments, all these, the fourfold crystal symmetry about
Sorry
001.
for interruption, madam. I think we are not getting the audio of the media that is being played.
Oh, it's not audible. Okay, so I'll just explain. So we have this, the red line that we see, this is 001 axis. Okay, so 001 axis. When we rotate it 4 times, right? So at least you can see the video as I talk. Yeah. So 1, 2, 3, and 4. So these 4 rotations, when these 4 rotations happen, the cube looks exactly same. And that sort of symmetry argument is used, that is the symmetry argument that is used to reduce the energy terms. Now we have threefold crystal symmetry about 111 axis, and similarly we have twofold crystal symmetry about 110 axis. Okay, so all of these, I'm not going to go into the details of this, but I would like to show at least one example of how this reduction is done. So these 3 symmetry operations are corresponding to a cubic crystal. And where do we go? Yeah, so before we even go into a cubic crystal, one thing that is well known to us is that it's invariant. The energy has to be invariant under reversal of magnetization. So plus m minus m should not matter to the energy, right? So so that is one thing. When we do that, then what happens is all the odd powers will drop out automatically. So then the magnetocrystalline energy can only have even powers of mi, of the direction cosines mi. Okay, so this one argument gets rid of half of the terms. Okay, now for the first non-vanishing anisotropy tensor, so we'll go back to that expression that I had earlier. So this right here. So there is a constant term. Well, that is that has to be determined from experiments. This the first order term and the third order, these are 0 now. But the first non-vanishing term Kij, can we say something about Kij given the symmetries? Okay, so that is what. Yeah, so that is what I'm going to show here. So Kij, K11, K12, K13. So let's say, one of the 3 symmetries that I had shown about, that I had shown earlier. So let's say I want to apply the threefold rotation symmetry about 111 axis, right? So we'll have to first obtain the rotation tensor for this, which I had done, which I'm just giving here without proof, that this R is 001, 100, 010. Okay, so the rotation tensor for this symmetry operation works out to be this. Then for a physical property to have this symmetry, to have the symmetry such that this threefold rotation symmetry about 111, it should remain unchanged. The Kij should remain unchanged under this rotation R. Okay, so what I'll do is this, we'll try to calculate this this 3x3 matrix by just doing this R transpose KR. Sorry, I don't think the indices should be there. This is an incorrect representation. But so when we do this transformation, we will end up getting that the only way this will happen is if K11, K22, K33 are all equal and equal to A, K21, K32, K13 are equal to B, and similarly K12, K23, K31 are equal to C. Okay. Then moving forward, now we can apply the 90-degree rotation, 90-degree or the fourfold rotation about 001 axis. Okay, in that case, the rotation tensor is something like this: 0, -10, 100, 001. Okay, and then when we apply that, the same symmetry arguments, that K should remain unchanged under this transformation or this rotation, we end up getting that this will only happen if Kij is just your diagonal tensor with all the 3 components equal. Okay, but what happens is that once we use this result in the second term, Kij, Mi, Mj, we will end up noticing that so this term, so only non-zero when I is equal to j, right? So we will have K11 M1 square plus K22 M2 square plus K33 M3 square. But then we found that K11, K22, K33 are all equal. So we just end up getting A times M1 square plus M2 square plus M3 square. Notice that we already know that M1, M2, M3, and M is a unit vector. So then this is simply a constant. The second order term just reduces to a constant. Okay, so that is why in the free energy model, there is no, in the magnetic crystalline energy, there is no second order term. This is just submerged into the constant. Okay, so this term is just so the constant term sort of incorporates this as well. Then the least order, the or the smallest order here is the fourth order, and then we have sixth order and so on. Okay, but then really we don't need to go much farther than this. These two terms are usually enough for us to explain the underlying physics. Then if we further want to allow dependence on temperature, then we just make these constants also functions of temperature. They will vary as we vary the temperature. Okay, so this is how we go on to reduce the the magnetocrystalline energy. Then let's look at the magnetocrystalline energy for different types of for different combinations of these values, right? For K01 and K1 equal to 2, K2 equal to 0. So these are all progressively like 0 order term, first order term, second order term, and so on. So the interplay between these values actually changes the free surface. When I say free surface, in the absence of any magnetic field, don't apply any magnetic field, we just plot the energy on its own. Okay, so we just plot this term on its own, the first 3 or 4 terms. And this is where the definition of easy axis also comes through very nicely. What happens is that there are, when I plot the magnetocrystalline energy, there are clear minima. Okay, so we can see that there are, so in this case, for this combination of constants, material constants, assume that this is non-dimensionalized, so we can sort of play around with these values. So so we can see that for this combination, there are minima along 100 directions, right? So 100, 010, 001. On all these directions, there is a minima, like a local minima in the energy. Okay, and then there are peaks along 111. So the easy axis clearly is the one that minimizes the magnetocrystalline energy, and the hard axes are the ones where magnetocrystalline energy is the maximum. Okay, so so for iron, this is for iron and iron based alloys like galphanol, this is the sort of energy surface, free energy surface. And for nickel, this is the type of free energy surface that we see. Okay, so so yeah, with this motivation, then how do we develop so I just talked about what energy minimization when there is no magnetic field. But once we apply magnetic field, all the energies that I talked about previously, or when we apply a stress, several of those energies become non-zero relevant. Then it becomes minimization of the total energy, right? So all these terms, the interplay between all of these terms, and then the resulting minima from that, it is how we calculate the total calculate the magnetic moments within each magnetic orientations within each domain, and then to calculate the total magnetization, which is sum over all the domains, right? So response of all the domains. So when we minimize the energy in terms of the same, right? I mean, we take m1 equal to sine theta cos phi, m2 equal to sine theta sine phi, m3 equal to cos theta. Just we go ahead and minimize it such that at theta equal to theta naught and phi equal to phi naught, del u by del theta is 0, del u by del phi is 0. And then to ensure that the result you're getting is a minima, then we have to additionally impose these constraints, right? Okay, so here, so these equations are fairly straightforward, and by taking polar angles, we are getting rid of constraint, right? Otherwise, we'll have to do a constrained minimization. So we'll have to introduce an additional parameter. But still, despite this, given the nonlinearities that are involved in the term, this approach becomes very messy. And also because we are dealing with theta and phi, so we'll have to first when we just do a when we just apply first derivative 0, when we apply just the first derivative 0, you get minima, maxima. There is like a whole lot of solutions, and then we have to avoid redundancy. So we have to make sure that you only pick thetas and phis within the certain range, 0 to 2 pi and 0 to pi and so on. And the sorting, it becomes a big issue. Okay, but we did this, we solved it using this approach, the same thing, and we compared this with the approach that we used in our group, which was to do this, like locally linearize the free energy about each easy axis. So what we did was, take the free energy term, define it within each domain, and then do a linearization about the easy axis. Do a linearization about the easy axis up to, sorry, here we won't do linearization. The free energy for for linear response, the free energy has to be of quadratic order, right? So we will take the Taylor series expansion up to quadratic order, and we will keep the constraint. Okay, so we'll keep the constraint. So this is a constraint minimization. We'll do it in terms of magnetization, because of, we wanted to avoid the whole mess of dealing with angles, duplication of angles. So then we do a Taylor series expansion of the free energy about CK, and then do a minimization within each domain. So this gave us, all the solutions to this will give us the orientation of M for a given applied magnetic field direction. And then finally, what we end up getting is a nice linear equation where this K, this matrix K and this vector B only depends on the applied magnetic field and applied stresses. Okay, so and then magnetostriction is defined in terms of magnetization. Again, this is reduced through careful symmetry arguments. For a cubic crystal, magnetostriction, I have only written the 2D components here, but so this is what we get. And then we get the magnetic moment orientation within each domain, and then we calculate the volume fraction of each domain. So if we remember correctly, I was saying that, for a certain applied magnetic field, some domains grow, right? So the volume fraction occupied by certain domains will be larger compared to some others. So that is calculated using statistical mechanics. Again, something that, I have skipped over, I have not talked about, but that comes in through this term. The volume fraction is calculated through Boltzmann averaging, what's called the Boltzmann averaging. Then we sum up the entire response in this manner. We calculate the magnetization, as I mentioned before, by doing this local linearization and then minimizing the energy. That gives us all the magnetic moment orientations of each domain, and then we sum up. We calculate the domain volume fraction using the statistical mechanics based averaging, and MS is a known constant. And then we calculate magnetic induction, which is nothing but mu naught H plus M. That's a universal equation. Then similarly, total strain, S compliance, this is the compliance matrix. So interestingly, here the mechanical response is linear. If I only wanted to, if there was no magnetic field, stress versus strain behavior is linear, strains are infinitesimal, and all of that still works. Okay, so then the second term is the magnetostriction. Again, this depends on magnetization. So once we solve for MK, we get lambda K within the domain, and then we sum up again using Boltzmann averaging. Okay, so this, then we compare this with the nonlinear model, right? Our model, nonlinear model. As one can imagine, the model worked really, really well along the easy axis, right? And we were considerably faster. The same plot, if I do it using the nonlinear method, and we are using the same software, we did both in MATLAB. The nonlinear minimization took us 20 minutes, to develop a plot like this. Whereas using our code, as one can imagine, because you're only linearizing and then summing up the response, it took us a few seconds, right? And so we were able to get B, magnetic induction versus magnetic field, magnetostriction lambda versus magnetic field. So and then also we had to, actually there is yeah, so then we also did this as we keep moving farther and farther from the easy axis. So 100 being the easy axis, when the field was applied at moderately moderate axes. If you remember, there was a hard axis, there is an easy axis, and there is a moderate axis. Even at moderate axis, there was a lot of success with the model. Still the same level of computational efficiency that we observed before. Yeah, so this is what I was talking about. Now, whereas once we go farther, as you can see, as we move farther from the easy axis, we were seeing that the curve after saturation, post saturation, we are seeing digression. Okay, and this was even more prominent. Actually, I don't have that plot here. This became more prominent as we went to 111 actually. Okay, so so this is, I mean, this is the output. And then we also did, so this is called the actuation behavior. So when we apply magnetic field and there is magnetostriction generated, so this is the actuator response, actuation response, and there is the sensing characteristics where we apply stress and we look at what happens to strain and what happens to the magnetic induction. So clearly, even with stress, there is a saturation that happens. So after a, so this is, so we keep varying, we keep increasing the stress for varying magnetic field values. Okay. And in this case, the same thing again, we keep varying stress for varying magnetic field values, but look at what is happening to strain. What's interesting is, we can see here, what's interesting is that the two bounds, meaning at zero magnetic field and after saturation, the behavior is straight, right? I mean, this is our typical linear elastic behavior, but then in between, there is a non-linearity. Even in the stress strain plot, the non-linearity because of the applied magnetic field. All of these actually, our results match very well with the data that is available, experimental data that is available in literature. Okay. Now, so given that we have, I mean, we are out of time, I will stop here, but I just wanted to show, like, we were able to do this finite element implementation also successfully using the model, and our results match with existing literature. And our speed was heavily improved compared to using the nonlinear model. Like, there are times when the nonlinear model doesn't converge, whereas now if we use our model, our locally linearized model, we are able to get very good results. And we never had to worry about the fact that what if the magnetic field is far away from easy axis, because typically we design devices in such a way that its performance is optimized, and that can only be done if you're applying magnetic field or stresses aligned with the easy axis. Only then we get the maximum performance from the device. Okay, so with this, I'll stop my my presentation, and I'll take some questions. Yeah.
First of all, I truly congratulate you for enchanting us with the kind of subjects which we really search for it, for material science and mechanics in a different way. But one or two fundamental doubts, madam, because
sure. See, so since I'm not from material science background, so there are times when we don't see it from that perspective. But yeah, please.
It's a coupled subject, but still one or two very simple way.
Sure.
Please tell me, what is the volume scale you are talking? For example, you are talking about saturation, you are talking about no saturation.
Yeah.
There's a non-linearity. Which mass scale you are talking?
So the scale at which this was done, or the scale at which we developed our model, that is macro. So this is a macro sample only. The volume, so the sample that we take, one can see from even here. So it's roughly 50 mm, 100 mm length, and the diameter will be few mm, 2 mm, 3 mm, like that. So yeah, so it's a macro sample, fully macro sample.
Okay, madam. Now, if it is the case, I will ask only one question, madam, to understand only. See, for example, let me assume that I have taken one spherical ball, a thin spherical what you say is shell, spherical shell. I filled with the pressure. Hypothetically, I am filling with a small balloon sort of steel or whatever ferromagnetic material. I filled with pressure. That means it is some uniform Coop stress everywhere. This is PR by 2H. So now such a ball, if I keep it in the magnetic field, whatever you do, you can see the scenery of the strain growth. What will be the shape after seeing certain cycle of magnetic field? Can you give a small picture to me? I hope you understood my question. You take a small.
I understand your question. Actually, we may need to do some analysis here, but one thing that I can think of mechanically, really it has to be uniform. So if there was no magnetic field, right? If only pressure, we are applying only pressure, then whatever change in shape. No,
What I
no.
say,
Let me just deductively I'm doing it. So if it's only due to internal pressure, then there will be isotropic expansion. But if we apply magnetic field, I think it would matter how the, uh, so how the easy axis is oriented relative to the sphere. So for example, here, I think I stopped sharing my screen. I will share it again in this presentation. And again, I may not be able to answer your question satisfactorily, but I'll try. Okay, so the goal
Yes.
here, as we can see this rod sample here, it is very important to identify what is the direction of the easy axis. So the way the sample is cut becomes very important. So now let's say that we have in this case the easy axis, or the 100 axis, is along the length. So then there will be, this there will be a strain and the rod will stretch. Now if it is in case of sphere, then there may be some easy axis, and if we are applying magnetic field along the easy axis, then we may probably see that the sphere is getting elongated, becoming like an ellipsoid or something. But I mean, we may need to do some simulations.
okay,
It's not
okay,
because
madam. If
there is
the
a
case, yeah, I
yeah
understood. I know
yeah
that
yeah
it's
yeah
difficult if you really model it. Will you
yeah
get
yeah.
ellipsoidal?
Will I
No,
huh?
suppose
Uh-huh.
I am imposing my requirement. The
Okay.
final configuration after subjected to some sort of directionally as well as the magnitude wise,
Yeah.
some scientific way,
Uh-huh.
whether you can make whatever shape I defined to. Initially I press spherical, but I want ellipsoidal, permanently ellipsoidal.
Huh.
Can
Okay, so
you madam, by this?
can we make it permanent?
Permanently a shape which is ellipsoidal.
Um,
At least
so
not,
so you're
for
saying by doing so, just by applying magnetic field, I don't think we can do that. So unless we let the magnetic field stay that way. Yeah.
0 to 1 in
Uh-huh.
between. Whether you, if I say one animation, it will go to. I am speculating from your talk that it can become some odd shape, again come back. It will go to. Can you show some animation of? You choose very interesting magnetic field surrounding that EC orientation. Can you show how the ball will try to deform, come back, how it goes? Some sort of things will give a very good feel about the complexity or interesting science aspect of this problem. Anyway, it is.
It's
I
a very
don't.
nice suggestion for us to take into account actually for a future problem. I think it's definitely an interesting problem to study. So what ends up happening is that when we are looking at geometries, right, we will just look at something that is 1D or even 2D, where the magnetization is, the favorable directions are along the length or along the thickness in order to get the best actuator. But something like this, having a sphere and then looking at combinations of magnetic field direction and different types of so for example, this type of magnetic field that I'm showing here in this figure can be done by having a coil surrounding the rod, right? But if we have say a current carrying wire, right, in case of the sphere example, let's say passing through the center, if we have a current carrying wire, this will produce an azimuthal field, right? An azimuthal field which is not uniform, which will be non-uniform with strength decreasing as we move farther from the wire, but that will give a very nice magnetic field distribution, and that will be totally worth studying. What happens to that to the sphere when we have different types of input fields. Yeah.
Through scanning of, we are scanning some they are scanning by MRT scanning. If you are hypothetically one spherical ball is with a pressurized ball is moving through scanning. So when you watch, if in case you watch what is happening in the path of travel, whether the spherical shape, how it is distort, again it comes back in a one or two cycles. There's some sort of things. You can think what I'm the MRT scanner. If the small balls travels and come back, what you will get out of first cycle, second cycle, third cycle? You called about histories, and professor asked also the non-linearity coming back. So what happened when it is 10 times travels here and there and 5 times? Maybe it may be 1 meter or 2 meter, maybe the length, in MRT scan. So 1 meter travels, again come back. You can assume. So it is only a very some sort of question, but I don't want to take more time, madam.
No. Please, sir. It's a very nice question and very insightful questions. I mean, Yeah.
Can I assume that if you keep any material under the magnetic field with a stressed condition, if I again remove it, the magnetic field, you please tell me the time scale, whether my Poisson's ratio will change.
No, I don't think the Poisson, at least like, for the anesthetic model, and which is what we work, most of these devices, the range in which they work, the material property doesn't change by applying magnetic field and removing it. Yeah.
How long? Even if you keep for quite long time.
I don't know that actually. That part I will need to check with you about. But I do know that in case of, they make permanent magnets like this by keeping a magnetic medium, by keeping a ferromagnetic material in a very large magnetic field, which is post saturation field for days together, and then there is some heat treatment that is involved. I don't know the details of it. Really a little bit out of scope, but it is possible to sort of fixate that, and I think that may change the mechanical properties also. It may happen.
Asking with the physical for practical relevance. Nowadays we are talking about nuclear. I am from nuclear. That we are talking about ferromagnetic bearings. To support the bearing without any contact. Non-contact bearing is to when bearing rotates. It's a very heavy magnets, highly magnetized, and it is supporting the very big load. So now whether this property over a period changes only, with that motivation I asked, because people are using ferromagnetic bearings in the real application for rotating the thing without any contacts. They don't want contact, they don't want any oil. The oils are not good for some neutronic point of view. So this is what I ask. Anyway, madam, I don't take much time because there may be many people may be asking some interesting questions. I stop here. So really, I congratulate you. I enjoyed after a long time such a talks. Thank you very much.
Thanks a lot. Yeah, thanks for the very insightful questions.
Dr. A.K. Singh, you may please unmute yourself and ask the question.
Sure.
Yeah, madam, just I was curious that finally how many equations you end up in after the modeling, including the physics, material science, and mechanics, which you have finally solved.
So
that I want to see the system of equations. Yeah.
So okay, so actually I didn't have the time to go there.
Just
I have it somewhere.
I can read your papers.
Let me
just I'm curious.
No, I'll just I think this slide sort of sums it up. So we have our conservation of linear momentum. So if we want to count the exact number of equations, those will be 3, right? And then we have Maxwell equations. See, here we reduce it significantly because curl of H equal to 0 when we take. So this is if there are no volumetric currents, and that usually doesn't happen, right? So there is no, we don't give any volumetric current. So this is 0. So then here we automatically, we do this even for electric field, we will take a potential, right? So scalar potential, which is nothing but, so my gradient of that potential minus is equal to H, right? So that by doing that, we are actually getting rid of this one. So there is, then divergence of B equal to 0 is one scalar equation. So we have 4 equations in total, one magnetic variable phi, one magnetic variable unknown phi, and then depending on the mechanical loading and everything appropriately, like, you'll have the stresses and strains, and then the constitutive equation. There will be 2 sets of constitutive equations. One, the magnetic induction in terms of magnetic field and strain or stress, applied stress, and stress in terms of strain and magnetic field. So so that is the total combination. All the
so seven variables, seven variables. So we need 7 equations. Correct?
Exactly. Yeah. So all those, but then everything that I talked about, by doing the energy minimization, our goal is to get these constitutive equations, the coupled constitutive equations. Yeah. So
yeah, fine. Got it. Thank you. Yeah, we got that.
Yeah. This is the slide. Sorry. So this is the constitutive equations. Yeah.
Correct. Yeah. Thank you.
Thanks for the questions. Yeah.
I have a small question, madam. So are there also polycrystalline materials, magnetostrictive materials?
Yes. So there are polycrystalline materials. So I have not talked about that in this case. So what we see here, so in polycrystalline materials, then one has to do an averaging across the the different orientations. But here, so that is something that I have not talked about, but they do exist. Yeah. So in fact, a lot of the commonly found, if we want to purchase a magnetostrictive material, it's usually polycrystalline.
So can we alter K1, K2, K3, for example, to get a spherical field and directly use it, directly use your model?
So we can, yes, I think we'll have to modify the material constants to be able to use exactly. Yeah.
Okay, thank you, madam. Thank you for
Thank
the very nice lecture.
Very good evening to all. Welcome back to the session. Today we'll be continuing the previous lecture on unified mechanics theory. I welcome Professor Jamal to continue the session. Thank you, sir.
Okay. Thank you very much for joining this evening again. It is evening for you. It is morning for me. So yesterday I stopped at the coordinate system in the unified mechanics theory. And then we said we have a linearly independent axis called thermodynamic state index axis, in addition to XYZ time coordinates. Now, so why do we need this axis? First, the thermodynamic state index axis is linearly independent. It means that the information on this axis cannot be represented on XYZ or time. And another reason is time can progress without any change in the thermodynamic state index axis. As I said, also mentioned yesterday, for example, at 0 Kelvin. But there are also many other examples where time can progress entropy without progressing. And then you can also change XYZ coordinates without any change in the thermodynamic state index axis, like a rigid body motion. If a body moves from point A to point B as a rigid body, there is no any entropy generation in the system itself. Its location will change, time will change, but there will be no entropy generated in the system. But however, if the thermodynamic state index coordinates change, then XYZ time must change. Professor Arthur Eddington once said in an article, I think Science magazine, entropy is arrow of time. Essentially, the XYZ time coordinate system depends on entropy. If entropy moves, they have to change. And again, thermodynamic state index coordinates cannot be represented in space-time. So let's look at some examples. This is a YouTube video. Unfortunately, we have a snowstorm here, so I had to stay at home, and at home my internet is slower. I hope you can see this video. Now, according to Newtonian mechanics, XYZ time, a straight line should be the shortest distance between 2 points, and it should be the fastest if we are using the Newtonian mechanics. But actually, it is not. So the motion of the balls here, we will release some balls from the top, and we will see that the longest distance will reach the bottom first, which completely violates Newton's description. But however, the one that is progressing along the thermodynamic state index axis, where phi is 1, will reach the bottom first. See if you can watch it. Are you able to see it?
Yes, sir.
Okay. So as you can see, let me go to the next. Wait a minute. I could just my YouTube took over my screen. Okay, actually, let me see. I was gonna show this anyway. Another video here, then I will explain it. So this experiment, okay. You see, the ball that is coming from the shortest distance, which is the straight line between the 2 points, is not reaching the end first. Now, keep in mind that they all start from the same potential energy level, and the kinetic energy of the balls at the initial point is 0. So the initial energy level for all 3 are equal. So if you use, for example, essentially Newtonian mechanics based on the laws of motion and Hamiltonian or Lagrangian, the one that is going in the straight line should get to the end first. But actually what happens is the ball that is going over the longest distance, it is moving fastest along the thermodynamic state index axis. And the thermodynamic state index 0 at the beginning, and then thermodynamic state index is 1 when they reach the bottom. So the distance doesn't matter. The entropy generation rate and the speed along the thermodynamic state index is what matters. Now I have to somehow get rid of this YouTube because it took over my presentation. 1 second. Okay, yeah. And now let me go. Okay, this is you watch this one. Now, some of you asked yesterday, it might be difficult to derive the thermodynamic fundamental equations. Yes, they are not, I cannot say they are readily available in any textbook or you can derive them in a month, because you have to understand the micro mechanisms controlling the process in the material to be able to derive these fundamental equations. Like, as I told you, in the last 30 years, my primary research has been studying mechanics of computer chip reliability and their lifetime prediction. So like, for example, for a computer chip solder joint, you have thermal, mechanical, electrical, and chemical loads acting on a chip. And the critical point, the failure point, is always the solder joint. And this is the, for example, thermodynamic fundamental equation for a solder joint subjected to thermal, mechanical, electrical, thermal gradient chemical loads. But if you have a system where you only have stress and strain, this would be your thermodynamic fundamental equation. So it can be very simple too. And of course, you know, we are deriving more and more equations every day, us and other groups around the world. So we don't reinvent the wheel. We use what has been published already. Okay. I don't know why my so next. Okay, so I want to show you some experimental verification of this work. You will have also other researchers presenting very good lectures on experimental verifications of this theory by Nushad bin Jamal, who just finished his PhD at IIT Madras, Xiao Wei Li, who is about to finish his PhD in Buffalo. But I will show you some results from other groups in the US and around the world. Like, for example, if you take a simple bar, according to ASTM standards, and then test it under tension, compression, cyclic fatigue loading. And of course, this is you initially start here, and then material, as the material degrades, normally we define the slope of this stress strain diagram as the elastic modulus. As the material degrades, the elastic modulus degrades, and then finally it will break. Now, we can calculate the entropy generated in this system from this stress strain diagram. That will be pretty much the area, total area inside this hysteresis curves divided by the temperature and mass density. And if you plot the thermodynamic state index from 0 until it fails, you see it goes from 0 to 1. And then when close to 1, it fails. Of course, this is a exponential function based on the mathematical derivation. You can never reach 1 in an exponential function, but you get very, very close. It is like 0.999, something like that. So this is for a cyclic loading. If you look at a monotonic loading, again, we have a sample A36 steel ASTM standard, and we apply uniaxial tension on the sample, and we plot the stress versus strain curve. And then this is the stress strain diagram we get from the testing. And then from here, we can calculate the thermodynamic state index. We see that again, that goes from 0 to 1. And initially, it stays very close to 0, but there is something here in the material, passes a critical point, and then starts to increase significantly. But eventually, at the failure point, again, the thermodynamic state index is very close to 1. This is a paper by Professor Fonsari from Louisiana State University. It was published in the Proceedings of Royal Society. He again does cyclic loading on ASTM standard samples. Here he is testing aluminum samples. And then this axis is the entropy at the failure point, total entropy at the failure. And this is number of cycles to failure. And also total entropy and number of cycles to failure. Now, what are these black circles? I don't know if you are able to see it, but I have black circles, black diamonds, circles that are blank inside, triangles blank inside. They represent different loading rates, loading frequencies. So to vary the different geometries to very many parameters, see if the total entropy changes when you change the loading or the geometry of the sample. Here, they find out that the total, what they call here fatigue fracture entropy, is constant, is independent of the loading or material geometry properties. But of course, it is a material property. If this is for aluminum, if you test cheese, you are going to get something else, a different entropy value. So as a result, they conclude that a thermodynamic approach for the characterization of material degradation, which uses the entropy generated during the entire life of the specimens undergoing fatigue test, is used. Results show that the cumulative entropy generation is constant at the time of failure and is independent of geometry of the sample, the load level, and the load frequency. Like, for example, if you use Coffin-Manson equation to curve fit to fatigue data, you have to get different parameters for different load levels, for different stress levels, and then also different mean stress values. So you will need a different polynomial Coffin-Manson coefficients for different load levels, different load frequencies. Hey, I'm sorry, I have to take my dog here 1 second. What? No. And then there is another nice work by a group in Poland. They published a paper in journal Plasticity. They compare the traditional damage mechanics model with unified mechanics theory. And of course, in the Chabosh-Lemaitre ductile damage model, there are, I think, 17 material constants obtained from empirical testing to curve fit damage potential. But in unified mechanics theory, there is no damage potential. Our number of constants is 0. So their conclusion is the results indicate that dissipation-based fatigue damage modeling, UMT, unified mechanics theory, leads to better fatigue behavior predictions. This is from their paper in the Journal of Plasticity. I think Nishad is going to present this, so if Nishad doesn't mind, I'm going to skip his data. This is a work by Professor Mohammed Modarres at University of Maryland in College Park, where he uses this theory for predicting corrosion, fatigue. So in the experiments, they have samples, they subjected them to corrosion and also fatigue. So this is the setup they have, where the sample is subjected to fatigue and also corroded. They conclude that we therefore conclude that entropy generation can be used to assess the degree of damage, the amount of the life of materials expended, and the extent of the life remaining. Professor Mudaris also published a paper on structural health monitoring. Again, for predicting life of metals used in structural application. And then he shows that the fatigue fracture entropy at the failure point remains in a narrow band. So he tested multiple samples for every stress level, every geometry. Now, you might say, how come there is not a single value at the failure, but a band? Because when you do an experiment, you are not actually testing exactly the same samples, okay? The next sample will have different amount of dislocations, will have different boundary conditions. There will be always variation from sample to sample. Little bit, but not much. So if you look at the band, it's a very narrow band.
Professor?
Yeah.
So, does that mean that the dislocations actually change the constituent of a material? Because as you just said a couple of minutes back, that that the entropy value at the failure, it does not depend upon the material.
It depends on
it depends on the material, but it does not depend on the geometry.
Yes, yes. So there will be small variation. Like, for example, you can buy steel, let's say for $1 per pound or $10 per pound. The difference is the quality of the steel. Okay, the $1 per pound is going to be very low quality steel and will have defects, significant amount of defects. And the one they sell it for $10 a pound will be very high quality steel that is probably used for like wristwatches, right? That will be very, very high quality steel. So of course, the amount of defects in the material is going to make some difference.
Okay, sir. Understood your point.
So may I just add, want to get one clarification. For example, your high cycle fatigue, which is basically a stress control. I'm talking about mostly on the basis of test data, clearly shows that the fatigue life is function of the size of the specimen. You know, it's well proven. So if you take a thin specimen, thin rod, and if you take a thick rod, the fatigue failures are very much different. I'm talking about high cycle fatigue. It's not applicable for low cycle fatigue. So high cycle fatigue damage is strong function of is one of the functions of the size effect. So can you give some clarification what you told? It's not function of the geometry.
Okay, so when you do high cycle fatigue, okay, and then you are comparing stress strain diagrams, and you say the stress strain diagram or the number of cycles as a function of stress is dependent of the size of the sample, right? Right?
About the fracture at the end of the life of the high cycle fatigue is probably actually it is a strong function of the size. If we take a smaller size, take a bigger size, the life what we are getting from the test data is quite different. It's known. We know its size is playing a lot of role. Yes, thank you.
Okay, but what are you comparing? You are comparing stress versus number of cycle, stress versus fatigue life, right?
Yeah, basically we talk about the alternating stress intensity. We call alternating stress amplitude. SN curve. We call SN curve. Okay.
Okay, so you are comparing the alternating stress versus number of cycles, right?
Yes, please.
Okay, but what we are saying is, if you compare entropy, failure entropy versus number of cycles, you will not see that variation. Here is an example.
It's but not measurable. For example, for me, the stress for engineering point of view, the stress is measurable. We can measure load by area in a generic sense, particularly when high cycle fatigue. It's not much change in cross section. High cycle fatigue failure is without much geometrical change. So force by area, whereas the entropy calculation high cycle fatigue, I don't know because I know insight about this, but people should see in a real application point of view. Scientifically, what you say, very good, mechanics point of view. But in engineering point of view, for me, very easy to get the life SN curve. I think people were living with several decades on that.
Okay, so on
just
Tuesday,
want to get some answer. I'm not counter-argue with you, but I want to get some answer from you for this question.
Yeah, so on Tuesday, my PhD student, Mr. Xiaowei Li, he will give a presentation on high cycle fatigue and also on ultra high cycle fatigue. And then he will answer all the points that you raised. Okay?
Thank you very much. Thank you.
You're welcome. So here is another paper from Michael Khonsari's group at LSU, published in Theoretical and Applied Fracture Mechanics. So what they do is, again, here they tested aluminum alloy for different loading conditions, loading frequency, and sample geometry, different size samples. And then they plot the fatigue fracture entropy, megajoule per cubic meter at Kelvin versus number of cycles. Now, the samples are breaking at different cycles, like you said, okay? So the fatigue life is changing. Fatigue life is changing. Like this sample broke at 10 to the power 5, I don't know, 0.5, 10 to the power 5. This sample broke 1 million cycles. So the life is different. But however, what is not different is the total entropy, and that is here. Now, the stress level for each one of these is different, because we say the loading, because if you are comparing same loading, you are not doing anything scientific. You are applying the same load again. You are saying they all, no, we have, like, for example, the load, the average mean stress level for this sample is, of course, smaller than for this one. So that's why this one is failing earlier, because the stress is higher for this one. And this one has a smaller stress. As a result, it fails in 1 million cycles. So if you plot a SN curve, you will have here, if there are 6 or 7 samples, you will have 7 different SN curves. But however, what is unique what is unique is the entropy, total entropy value at failure. They all fail when the thermodynamic state index is 1. So to answer your question again, if I took this data and plotted the ascent curve like you told me, because this one has a different stress level and this one has a different stress level, and this one has a different life, and this one has a different fatigue life, I will have 2 different curves, right? I will have 2 different curves. But what is not changing is the total entropy. That is the point they are making. Essentially, along the 5th axis, the thermodynamic state index axis, you are going just between 0 and 1. There was another paper from, some of you might know, Professor Ganesh Subbarayan at Purdue. I think he was from IIT Madras. His bachelor's was from IIT Madras. He's a professor at Purdue University now. He published a journal paper in journal Entropy. He says the developed damage models are shown to more accurately and consistently describe fatigue life than several alternative damage models, including Weibull distribution function and Coffin-Manson relation. This is another example from Professor Moderes's testing, again, for different, here I hope you see the colors. So each color represents a different parameter. He's either changing the stress level or geometry or the frequency of the loading. And then at the end, you have the total failure entropy, again, in a very narrow band. This paper was from Georgia Tech. They applied this theory. They implemented an abacus in a user-defined subroutine, and then used it for predicting fatigue life of a computer chip. So here, this is the chip. This is the plastic cover that you see. These are solder joints. These are the circuits. These solder joints carry information between circuits. You know, you have about 1 billion transistors, and this is zooming on this interconnect. And then this is cycles to failure, and this is delta C. Now, the loading on the computer chip is not mechanical. Unless you sit on it, it is not mechanical. It is temperature. So what happens is when you turn on your computer or cell phone, the circuits, the transistors generate heat. They heat up the unit, the chip. But however, there are many layers, but each layer has a different coefficient of thermal expansion. Each layer expands at a different level. As a result, these solder joints are subjected to cyclic shear when you turn it on and when you turn it off. And then continuously, they are subjected to cyclic shear because of this heat and cooling down when you turn it off. So this delta C is the temperature change in the ambient. And then of course, for different levels of delta T, fatigue life is going to be different. Fatigue life is smaller and the temperature is 300 degrees Celsius in the chip, there is more differential expansion. The shear on the solder joint is bigger, and it will, of course, fail earlier. So they have the experimental data, the green one, and then they have this purple one that they call entropy production, calculated using unified mechanics theory. And then these are from Coffin-Manson data. You know, Coffin-Manson data is obtained from an experiment, and then you use those coefficients for a real system. So you can see that the entropy production, it gives almost identical results as the experiment, but Coffin-Manson is far, far off. Because Coffin-Manson is obtained from a sample, not from the computer chip, and then used, essentially when you do the experiment to get the parameters for Coffin-Manson, you don't test the chip, you test just the material that you are using it for, like for the solder. And then you obtain the parameters. And then you use it for prediction. But here, as you see, they cannot predict. Here is maybe, yeah, this is better view. You can see the cycles to failure, delta T, differential temperature on the sample, the chip, the package. And this is the experimental data. This is the what they call entropy production. And these are Coffin-Manson 1, Coffin-Manson 2, Coffin-Manson 3. As you know, there are many Coffin-Manson models in the literature. People modify Coffin-Manson equations every day. But at the end, Coffin-Manson is just a curve fit parameter you get from the experimental data. Okay, there was another good paper by a group in Belarus, Professor Sosnovsky and Sherbakov. And they, in journal Entropy, they concluded that analysis of more than 600 experimental results allowed determining a unified mechanothermodynamic function of limiting states of polymers and metals. And they are also known as fatigue fracture entropy states. Essentially, they tested 600 samples by changing parameters, again, load level, average load, mean stress level, geometry, loading, frequency, like for example, also tension compression versus tension. Tension will give you different SN curves. If you test the same sample and tension versus tension compression. So that's why they ended up with 600 sets of data. Again, they end up with the same conclusion. And then this is another paper from Consari's group. Another result. Okay, so these are all same. This one is again showing the crack length versus the normalized cumulative entropy. So essentially, this is more like a fracture mechanics. For a given crack length, the required entropy to reach it. And then the cumulative count, which comes from the data, test data, and then this is the entropy for load ratio R 0.08 and frequency 3 Hertz. And then the results show that the evolution of the entropy estimate in the time domain correlates well with the evolution of acoustic entropy hit count. AE stands for acoustic entropy. People also applied this to batteries. And this is a group from Spain. They concluded that they published the paper in Journal of Energy Storage. We have introduced thermodynamic state index in battery degradation model. We conclude that entropy characterization is a promising tool to describe battery aging because it allows a simultaneous approach to capacity and power fade during aging. This group is from University of California in Los Angeles. They published a paper in Journal of Applied Physics. They say on the basis of entropy production, they provide a unified model for mean time to failure for thermomigration and stress migration. And in general, the input from all sources of entropy production should be taken into account simultaneously, meaning that the thermodynamic fundamental equation must account for all entropy generation mechanism. And then essentially they show that they have a link between mean time to failure and threshold entropy. This group is also from Spain. They use, again, the unified mechanics theory. They say we devised a methodology to monitor battery aging using internal entropy production. This group is from University of Texas in Austin. They published a paper last year in Electrochemia AICTE. They say degradation entropy generation methodology is experimentally verified via uncontrolled cycling of nickel metal hybrid batteries, lead acid batteries, lithium ion batteries, supercapacitor and fuel cells. Near 100% fit of experimental data to theoretical formulation persists in this study. So my time is up, and I have more experimental data from different groups around the world to show you, but I want to stop here and then take your questions because according to my time is up for today. Do you have any questions? Okay, let's go to the chat. There is a chat here. Is there an inherent assumption that the size of zone of damage is independent of geometry, loading rate, etc. in this formulation? Size of zone of damage. I'm trying to understand it. What do you mean zone? So the damage is distributed. It is not like in a single location.
Professor, my question is that if you are taking metals, probably the size of zone of damage is a point. And if you are studying a material like concrete, then the zone of damage is distributed. So if you are doing a test which is a very slow loading rate, then probably the zone of damage will be maybe small. And if you are doing it at a very high rate, the zone of damage will increase. So when you are formulating, say, entropy generation and all, you have to consider the amount of energy which is dissipated, and it depends on the zone of damage. So
yes, for those two cases, you will have different entropy generation mechanisms governing the dissipation.
Yeah,
they will not be same.
So for suppose if you take a structure with a distributed zone of damage, the loading rate might, depending on the loading rate, the zone of damage might increase. And when you're saying a constant entropy
at the failure,
means it may happen that the zone of damage might increase and it may take more energy than what is compared to a slower loading rate case.
No, it will not. It cannot. It is the amount of energy the system has. You can look at it this way. you have a limited amount of atoms in the sample, right?
Yep.
And each atom has a bond between its neighbors, right?
Yep.
So your total energy cannot be more than that. It is like you have $100 in the bank. You can go take $1 every day. It will last you 100 days. You can go take 10 cents a day. It will last you 1,000 days. You can take 1 cent a day. It will last you 10,000 days. But you cannot take more than $100. So the atomic bond between the atoms is limited. You cannot get more energy than what you have in the system.
My point is that the area over which the damage is occurring means more atoms are involved when the area of damage is more, and when area of damage is lesser number of atoms are involved.
Yes.
So
yes, but it doesn't matter because we are calculating the entropy as a density. So the density, the specific entropy is not going to change per unit volume. So essentially, let's say you have a 100-story building, okay? And then we analyze it with unified mechanics theory. Now, the columns at the 100th floor might still be all standing, but if the columns on the first floor failed, that whole building is failed, even though there is no damage in the 100th floor columns.
Yeah.
You understand? So once you put this in a finite element program, you don't have to have damage everywhere. It is just like the example I gave you. If you have a 100-story building, that will, let's say you just come and hit the columns on the first floor, okay, with a car, or let's say you crash into it with a car. There is no damage in the columns in the other floors. There will be zero entropy generated, but the building will collapse.
Yes, yes.
Yeah, so that is what you are saying is taken care of by the formulation in the finite element method. Because you still have to analyze the whole system with a finite element method. It is not just a single point.
Okay.
Okay, there is another question, I think. Are there any studies which are not matching unified mechanics theory? No, I have never seen a study that doesn't match unified mechanics theory. But if you can show that, that will be a wonderful journal paper. And I would love to see that paper. If you can disprove the second law of thermodynamics, actually, you might even get the Nobel Prize. Because that will be disproving the second law of thermodynamics.
Yes.
Professor?
Yes, sir.
Professor, can I ask one question? Actually, we say anyway, I will just, we are not disproving law of thermodynamics. What we want to say, we are giving, since you have taken example of Coffin-Manson relation. Let me take, have you compared ductility exhaustion theory for the fatigue failure? Ultimately, the accumulated the strain at a location, at whatever you say, unit per density, you know. So the accumulated strain energy density is ultimately the ductility, measure of ductility. So loss of ductility is one of the measure. Have we compared a loss of ductility when failure occurs, whatever unit volume you define, and what will be the thermodynamics? I think more or less nearly same. If you do really a detailed modeling, ultimately the hysteresis loop, you know, the energy, each hysteresis loops will say how much you are losing, how much energy is absorbed. So there's a limit. So we assume in Coffin-Manson relation, even if you do cumulative damage, ultimately we can derive, it is equivalence of the sum of the hysteresis energy, you know, every cycle by cycle, stable cycle, what is the energy associated with each hysteresis loops. So till a stable cycle is there, you just count how many loops afterwards it fails. then multiply number of loops. This is the total, that is once it crosses, it may fail, or the ductility, every time you are accumulating the energy, you are accumulating you are basically losing the ductility. Every history slopes, the plastic strain is getting accumulated. It is absolute adding. So once it reaches the ductility, maximum permissible ductility of the material, it fails. I don't find the, if you put isothermal condition, so I think more or less the unified mechanics theory and the ductility exhaustion theory and isothermal condition should be same. Why so much difference should come?
Yeah, so when you use the Coffin-Manson equation, like you have the plastic strain range, right? And
Yes.
then you have the test data, you must have the test data, and then you get the parameters A and B, which is the coefficient, the power over the strain. To get those parameters, you must have the test data, right? Without test data, there is no way you can get those coefficients. Here, I don't need a test data, number one. And number two, if the frequency is very high, like we also, Xiao Wei will give you a presentation on ultra high cycle fatigue. In ultra high cycle fatigue, actually, it is not the plastic strain that kills the material. The temperature in the material goes to 400, 500 degrees Celsius when the frequency of the loading is very high. So the as a result, in the ultra high frequency, ultra high life fatigue, it is not the strain. It is not, there is no plastic strain, of course, in the same sense. The entropy generation because of heat generation is the dominant factor. I don't think you can even model that with Coffin-Manson.
Yeah, Coffin-Manson is only for low cycle fatigue damage. We won't apply for high cycle fatigue damage. When Coffin-Manson relation is applied, basically we are taking as a functionality, the relation between the number of cycle and the delta epsilon P. Basically, it is a cyclic, the stabilized cyclic strain range, plastic strain range, which comes from, which definitely, if anybody wanted accurate life, he has to do a detailed the cyclic analysis, whatever advanced model, whether you use Sabouche model or any model, and try to get the epsilon P very correctly. If you predict, probably you are very close to the reality. Then basically one constant is related to the half of the ductility. You know, the A constant is nothing but ductility of the material divided by 2. You know, the first constant. And the second constant, what you say, index N, is definitely how much depth you are having, how much detail you are having on the deriving the cyclic histories loops. According to the N number can change. Definitely it can change. But for the designer, they used some number like 0.5, 0.6 or something. So that is fitting. N number is a fitting of the curve. But the first index A into or K into delta epsilon P power alpha, the first number K is nothing but half of 50% of the ductility, delta epsilon F divided by 2. So basically he says that if one half cycle, it can fail by the loss of ductility. If suppose N equal to 1, if you put one cycle, it has to fail. Naturally, the delta K should be delta epsilon by 2 only. No, I'm not questioning, because it is a well-proven subject. I want to hear from you your views. Why? I mean, researcher, yes, any researcher can do on the entropy. What is the unified theory? Many theories can be discussed. But ultimately, when it goes to the designer, how simple a simple designer can assess the life of the things on the disk table, you know, the design disk. How fast he can compute. Which truly speaking, I am not getting where you are now, where we are now in unified mechanics theory, and to reach that state, that across the table I can calculate and say this is the accurate life, which I feel in my own long experience, we are quite far.
Yeah, so like in the computer industry, the margin of profit is very, very large. So they always have fancy computers, all good engineers, So they use finite element method to analyze the system, and the reliability is very important for them. But on the other hand, like for example, in civil engineering industry, profit margin in the US at least is very, very small. Nobody uses finite element method to analyze any system. They don't even analyze it actually. They just give it to an experienced engineer. He sizes the members from architect's drawing. Actually, architect does the sizing. And then for them, here material is very cheap. And then they just run a small SAP analysis to show that everything has a factor of safety of bigger than 1. And then construction continues, which they start the construction before even designing it. So in the civil engineering industry in the United States, of course, nobody uses it, and I don't see anybody changing that practice. They will never use finite element method in the United States for civil engineering applications. But for mechanical engineering applications, like making a car engine or nuclear industry or aerospace industry or electronics, they use very, very high-tech methods. If they can, they will try to use quantum computing. So depends on what industry you are comparing. Okay, so is there any other question?
Sir, I have one. It may be a silly, it may sound a silly question, but
there are no silly questions, sir. There are no silly questions. There are silly people who don't ask questions.
I mean, nice statement that you have passed. Sir, for example, I'm doing a fatigue test, and from experience, I know that this sort of material will take these many cycles to get failed.
Yes.
Now, I mean, this fatigue concept and the failure fatigue has been related to the concept of entropy generation. But I really would like to know, can the fatigue failure be related to energy as entropy generation has been?
Well, entropy is energy unavailable for work. Essentially, entropy means that amount of energy you are taking from the material.
Right. So I mean, I just think that, for example, for a particular kind of material, if it fails by fatigue failure, it does not depend how many number of cycle it is undergoing, but the entropy generation would remain the constant, would remain the same.
Yeah, that
right.
is what
so
the test data shows.
Yeah. So can we say the same statement considering energy aspect? Can we say that it does not depend how many cycle a material undergoes, the energy will remain the same?
Yeah, because the unit for entropy is unit of energy, joule. So we are talking about the same thing. Entropy is energy, but it is just energy that has been lost, dissipated, not available anymore. So entropy itself is energy.
Okay. And sir, just a little more clarification, that if I'm loading a particular specimen, let's say at a rate, let's say the value of rate is X, and I'm loading it at 2X. So I'm just considering two cases where the rate of loading in one case is X and in another case it is 2X. So at the failure due to fatigue, does the total energy that goes into failure be the same in both the cases?
The total energy can be different, but the density of the entropy will not be different.
Yeah, that's the clarification I needed.
Yeah, the
Okay.
density of the amount of energy you need for unit volume of the material,
Yeah.
that is constant, that you can take out of the material. You can think of it this way. Let's say you have 1 unit, 1 cubic centimeter of wood or iron, okay? I don't care how you burn this material. You are not going to get a different energy from that 1 cubic centimeter of iron than what it already has.
Right.
So that is what you are doing. Essentially, when you fatigue the material, you can think of it as you are burning it in the wood stove. Okay, let's say you have locust wood, 1 cubic centimeter. Okay, you can burn it with a gasoline, you can burn it with benzene, you can burn it with a nuclear explosion. It doesn't matter. You can change the size of that wood, make it very big, make it small. The amount of energy you are going to get for 1 cubic centimeter locust wood is going to be same.
All right.
And I burn wood, so I know this.
Thanks for the analogies and thanks
Yeah,
for
yeah.
clearing.
Okay. I don't want to take up too much of your time.